Good afternoon. My name is Alejandro Ramos Romero from the Institute of Physics at UAP, and I will present to you our work entitled Numerical Study of the Optical Properties of Spherical Porous Gold Nanoparticles. Highlights. In this study, we investigate the optical properties of spherical porous gold nanoparticles, each with a radius of 100 nanometers and a radial distribution of a paraboloidal pores. We apply the discrete dipole approximation, or DDA, to calculate these properties. From the literature, we know that the synthesis of porous gold nanoparticles, PGNs, leads to a variety of particle size and pore structures. The most common size is around 250 nanometers, but there are reports of particles as small as 80 nanometers in diameter and as large as 800 nanometers. Let's look at the figure showing three PGNs obtained by three different synthesis methods. In image A, the one-step method produces a worm-like solid structure, creating channels between the pores. In image B, the growth method on lead sulfide nanooctaedras results in a branch-type particle. And in image C, the two-step method produces a more homogeneous pore distribution. All research aims to understand how porosity affects the optical properties of these nanoparticles. To do so, we use the discrete dipole approximation, or DDA. In this method, a particle is represented by a cubic array of endpoint dipoles. We assume a linearly polarized plane wave incident on the array. The fundamental DDA equation is P equals to AE. Here P contains the dipole moments of the end dipoles. A is the dipole-dipole interaction matrix, and E contains the local electric field at each dipole position. When we solve for the end dipole moments, we can calculate the particle's optical efficiencies, its near-field distribution, and the radiation pressure. The model we propose is a spherical porous gold nanoparticle of radius 100 nanometers. The pores are paraboloidal in shape and radially distributed. This geometry allows the pores to be elongated so that they all meet at the center, creating a hollow core. In other words, a hollow porous gold nanoparticle. The pores have a circular cross-section, and at the surface, the radius is 10 nanometers. To determine the number of pores, we analyze a image of a real PGN. We divide the image into equal-sized pixel sections, then use a Python program to measure the solid and pore areas in each section. Then we can make a reconstruction of the PGN. From this, we estimate a surface porosity of 30%. Based on this value, our dipole model includes 102 pores, giving a porosity of 25.6%, very close to the experimental one. In this work, the degree of porosity is defined in terms of the pore depth to the sphere radius ratio. When C equals 0, the particle has no pores, is a solid sphere. When C equals 1, the pore depth equals the particle radius, creating a hollow nanoparticle. We perform calculations for two surrounding medium, air and water, and also vary the material inside the pores, filling them with either air or water. I will highlight three main results: the optical efficiencies, the electric near-field distributions, and the radiation pressure. In this figure, we show the optical efficiencies of a spherical porous gold nanoparticles, where the porosity parameter C was modified. We can see that for each spectrum, the maximum is redshifted. For the absorption efficiency, the maximum increased with the porosity, and for scattering efficiency, the maximum value is observed at C equals 0.75. The absorption efficiency results show that as porosity increases, the LSPR shifts to the longer wavelength, is a redshift. Also, when the pores are filled with water, the resonance shifts further to the red compared to air-filled pores. The shift is due to a change in refractive index from 1 for air to 1.33 for water. This resonance corresponds to the dipolar plasmon mode. The electric near-field results and the LSPR wavelength show that porosity enhances the plasmonic response. In this figure, we present the normalized electric field for particles of different porosity. For highly porous particles, the hotspots appear both on the surface and inside the pores. For the hollow particle, the field is strongly confined inside the central cavity, producing an even larger enhancement than on the surface. This effect is linked to the sharp tips formed by the pore geometry, which are known to intensify electric fields. Finally, we explore the radiation pressure on the spherical porous gold nanoparticle. The radiation pressures arise from both scattering and absorption, but given our particle size, the scattering dominates. In this figure, we show the radiation pressure for A, particles in air with air-filled pores, and in B, particles in water with water-filled pores. As in the optical efficiencies, we observe a red shift with increasing porosity. Conclusions. In summary, the LSPR redshifts with increasing porosity. The plasmonic response is enhanced as porosity grows. In hollow particles, the electric field is mainly confined inside the nanoparticle. Hotspots are observed both on the surface and within the pore structures. The maximum of the radiation pressure spectrum also shifts to the red as porosity increases. Here is the bibliography used in this presentation. And that's all. Thank you very much for your attention.